All right, good morning, kids. This is called More Geometric Sequences. The start here is going to be a smaller review. I do want you guys to take notes and email me your notes on this topic. So to start here, I could give you, I tend to give the letter G when it's geometric, but I don't always do that. And if you see something in the book and it has an A, it may or may not be arithmetic, so don't be fooled by that. In this situation, this explicit formula is going to start at 5 and constantly double. There's a reason why they have to the power of n minus 1. I'll try to go through that quick. When you list out your terms, commonly, but not always, we start with n equals 1 and move on to 2 and 3 and so forth. By placing a 1 up here, if I put this 1 in place of that n there, the first thing I do, order of operations, I get 1 minus 1 is 0. 2 to the power of 0 is 1. 5 times 1 is 5, so I get a value of 5 here. That's good because I said that this was the initial value. This is your first value. This 2 tells you that you're constantly doubling. I mean, I could just fill out 10, 20, and so on and so forth for my terms of my sequence. But let's just check the math here. If I take this 2 and put it in for n, first thing I do is 2 minus 1 is 1. 2 to the power of 1 is 2. 5 times 2 is 10. So we have confirmation that we're constantly doubling. This explicit formula, it's not too hard. Let's say the book at some point says, please figure out the 100th term. You can use this information, place the 100 there, figure out that this is actually 2 to the power of 99. That's some very large number. 5 times that is huge. I mean, it makes sense that this is going to grow pretty quick. Graphically, these situations tend to start kind of slow and then really explode very quickly. So it's kind of easy to see that this thing would be a huge number. All right, the next thing I want to talk about is just a small little review of recursive expressions for geometric sequences. So the pattern is still going to have an initial value, and let's say double or triple or something have a constant ratio. And I'll do the same thing. We're going to start at 5, and we're going to constantly double. This means that to figure out the next term, take your previous term, I'll even put this in parentheses, and double it. So I've said the exact same thing. This is the exact same sequence. Your sequence would start with 5 and constantly double. Oops, almost forgot what 20 doubled was, so on and so forth. This time, though, if I ask you for the 100th term, that's way down here. If I say, what is G sub 100? Sadly, you have to take the 99th term and double it, so on and so forth. So this is really not a beneficial way to figure out future terms. This is just really, if you see a few terms, you could just say to yourself, look at this, we started at 5 and we're constantly doubling. Our ratio, our constant ratio in this instance is 2. So the generic way you would write the explicit formula, I mean, this is more like the formula is like such: G sub n equals your first term times your constant ratio to the power of n minus 1. If your first term is 100, there's a 100 here. If your constant ratio is 8, there's an 8 here. As opposed to the recursive method, I mean, this is kind of ridiculous. You state that your first term is your first term. That's kind of redundant. And to figure out your next term, you take your previous term, I'll put this in parentheses, and multiply by r, like such. So these two techniques are saying the exact same thing. They would have a first term of G sub 1, and the next term would be r times G sub 1, or r times times G sub 1, et cetera, et cetera, et cetera. You could say that G sub 2 is G sub 1 times R. That's a true statement, but that's how that would work. So now, if they gave you a sequence of terms, let's say they look like this: 150. You're not sure if it's arithmetic. Are we subtracting 50 each time, or are we multiplying by half? But now you get the third term, and it's clear to see you're multiplying by half. You could write this way if you'd like: 100 times half to the power of n minus 1. or recursively, you state your first term, 100, and then you state what's happening each time, times 1/2. And again, I like to put it in parentheses there. But they're eventually going to throw something like this at you. They're going to say that they have a geometric situation where you know your first term is 5, you're unsure about your second term, and you know your third term is 12.8. I'll show you. There's a few different techniques for solving this, and I'll show you what I do. I assume that when we multiply from here to here, we started at 5 and we multiplied by r. So I'll just put times r there. Whatever that square is, it's 5 times r. To get to the squared term, from this squared term, the second term to the third term, we multiplied by r again, multiplied by r. So now we can back up and say to get from 5 over to the second term, we multiplied by r twice. I can go times r times r. That's a true statement. 5 times r gets you to 12.8. So now it's just a relatively easy algebraic equation that we could solve. I'm going to rewrite this as 5 times r squared equals 12.8. I'll divide each side by 5. R squared equal, I'm not that good at math, 12.8, 25.6, let's just see here. Equals 2.56. And now I take the square root of each side. You could throw out, normally what we say is you have both the positive and the negative of the square root. We could throw that out. The answer is 1.6. Our constant ratio is 1.6. So now to see what the second term is, I'll take 5. G sub 2 is equal to my first term times my constant ratio, 1.6. That's 8. And if I take 8 and multiply by 1.6 again, I get 12.8. Everything checks out. And I can continue then to figure out, let's say, these future missing terms. But more importantly, I can state the equation here 2 different ways. My explicit formula would be 5 times 1.6 to the power of n minus 1, or the recursive way would be g sub 1 is 5, and g sub n equals g sub n minus 1 times 1.6, depending on what the book asks you. So let's say they give you something like this. They don't tell you the first 2 terms. They tell you that the third term is 100. They don't tell you the fourth or fifth term. And they tell you that the sixth term is 12.5. Sometimes the book doesn't lay it out like this. They will give you this sort of situation. They will just say your third term is 100 and your sixth term is 12.5. You'll have to know how to take this information here and make a chart like that up there. Just, it's a visual aid is all it is. But it's 2 ways of stating the same thing. And again, to get from the third term, which is here, over to the sixth term, we multiplied by r 3 times. We started with 100, and we multiplied by r and r and r, and got to 12.5. I'll rewrite this equation as 100 r cubed equals 12.5. And now I'll just solve for it algebraically. I think this is 0.125. And now we're going to do the cube root of 0.125. And we get, oops, sorry there. I'll do the cube root. And I get r equals half. Knowing that r equals half, we can actually do this math in our head. Moving forward, each term is half of the previous, so this would be 50, and that would be 25. And that checks out. That looks like 12.5. What you could do, though, is divide by half to work your way backwards, or instead of dividing by half, you could double it. So the previous term is 200 and the initial term is 400. So now based on all that information, we could write the sequence as g sub n equals 400 times half, or half as a decimal, to the power of n minus 1, or recursively, g sub 1 equals 400. And to figure out any term, you take the previous term and multiply it by half. So one more time, depends on what they ask you. If they ask for explicit, this is how you write it. If they ask for recursive, this is how you write it. Where am I at here? Alrighty. Have a great day. Take some notes. This is your very first assignment. This might be the biggest assignment you have all week.